Hey Extension 2, welcome back to Mathematics. We're starting off with a flashback question from the last video. This is a HSC question from 2015, 3 1-mark questions. Hit pause and have a go yourself before I run through the solution. Okay, for part I, we're finding the modulus of the complex number z, which is minus root 3 on the real axis and 1 on the imaginary axis. So if we draw ourselves a quick picture using an Argand diagram, we're going to have a point that's root 3 to the left and 1 unit up. Okay, so if we find the length of the hypotenuse using a bit of Pythagoras' theorem, we can do square root of 3 squared plus 1 squared gets us an answer of 4. Square root gets us 2. Okay, or you can recognize here we have our 1, 2, root 3 triangle. Either way, we get the modulus of z is 2 units. Okay, now like I said, we have our 1, 2, root 3 triangle, which means that our angle in here where the cursor is pointing is going to be 30 degrees or pi on 6 radians. So if that right there is 30 degrees, the angle with the positive real axis is going to have to be 150 degrees, which we can write as 5 pi on 6. So 30 in here, so 150 out here, which we'll write in radians, 5 pi on 6. Okay, so there's part I, and there is part I done as well. Now for part 3, we are finding the argument of z divided by w. To do this, we're going to use a shortcut that we looked at last week. We said that when you are dividing two complex numbers, the argument will be we can essentially do a subtraction, okay? So argument of z divided by w is argument of z minus argument of w. In part 2, we got the argument of z as 5 pi on 6. We have the complex number w up top here, and we can see it's already in polar form, so the argument is pi on 7. So all we need to do is 5 pi on 6 minus pi on 7, and we get a final answer of 29 pi over 42. So it's a nice quick answer if you know the correct method, if you've studied your content properly. Okay, today's lesson is all about powers of complex numbers and also looking at a new form of expressing complex numbers, which is called exponential form. Okay, first thing we're going to look at in this video is how we apply powers to complex numbers using a little thing called de Moivre's theorem. So if we have a complex number z equals r cos theta plus I sine theta, so it's in polar form. If we wanted to compute z to the power of n, where n is an integer, all we need to do is apply the power to the modulus and multiply the power to our argument. Okay, this comes from last video when we were looking at multiplication of complex numbers. We said that the moduli are going to multiply and the arguments are going to add together. So this formula here is just an expression for the repeated process of multiplying a complex number by itself. Okay, so as I said, the complex number needs to be in polar form. So best way to find a complex number to a power is put it in polar form and then apply de Moivre's theorem. Let's have a go at an example. Here's our first one. We have root 3 minus I as our complex number. We want to find z to the power of 7. Okay, like I said, we want to apply de Moivre's theorem. So first things first is we need to write our number in polar form. I'm not going to go through all the working for that because that was the focus of the last video and I want to try and keep these as brief as I can. So I'm just going to skip straight to root 3 minus I having a modulus of 2 and an argument of minus pi on 6. Okay, if you need more practice, previous video will be good for that. Okay, now we have it in polar form. Now we can apply de Moivre's theorem and say root 3 minus I to the power of 7 is going to be 2 to the power of 7. So we're applying the power to the modulus and we are multiplying to our argument. So minus pi on 6 turns into minus 7 pi on 6. Okay, now we can calculate 2 to the power of 7 to be 128. And now you have to be careful with your arguments when you're applying de Moivre's theorem because often after you've multiplied, your argument is going to be outside the range where we need it to be. Okay, again, from the last video, we said arguments always need to be from 0 to pi or from 0 to minus pi. If we look at negative 7 pi on 6, it's going to be just beyond if we were going anti-clockwise. Here is what a rotation of minus 7 pi on 6 would look like. Okay, so we've gone beyond the range of minus pi, so we can't say minus 7 pi on 6 as an argument. We need to instead look the other way and say from the positive real axis, we have a rotation of positive 5 pi on 6. Okay, so you don't want to measure beyond that 180 line. You don't want to go too far that way or too far the other way. Otherwise, it's not technically classed as an argument. Okay, so there's our final answer. That's our root 3 minus I to the 7 in polar form. Okay, we'll do another one. We can also use de Moivre's theorem for negative numbers because it works for all integers. We are going to show that 2 plus 2 root 3i to the power of minus 6 is a purely real number. So we're not expecting any imaginary components in our answer. Let's see how we go. First things first, we have to put it into polar form once again. So 2 plus 2 root 3, if we drew a little picture, we would see using Pythagoras, it has a modulus of 4 units and it has an argument of positive pi on 3. Okay, now we have it in polar form. Now we're going to apply our power of minus 6, which means we're going to do 4 to the power of minus 6 and we're going to multiply pi on 3 by minus 6. So now we have minus 6 pi on 3 inside of our argument. Okay, so we're going to have 4 to the minus 6 equals 1 over 4 to the 6, and we can calculate that shortly. Our arguments are going to simplify to minus 2 pi. Okay, now let's think about the values of cos minus 2 pi and sine minus 2 pi. So remember, cos of a minus angle, because cos is an even function, this will be the same value as cos of 2 pi, which is cos of 360. Okay, if you've done some sketching of trig functions in the advanced course, you know that cos 360 is equal to 1. Hopefully you also know that when we have sine as an odd function, so sine of a negative angle, we can just pull the negative out the front of the function and say negative sine of 2 pi. Again, sine of 360, if you think of your graph of the sine wave, at 360 sine is equal to 0. Okay, so the cos minus 2 pi is going to work out to be 1. And the sine of minus 2 pi is going to work out to be 0. That's convenient. That's going to get rid of our imaginary term, which is what we're trying to show with this question. We want a purely real number as our answer. So inside the brackets, we have 1 plus 0, and 1 over 4 to the 6 is just 1 over 4,096 multiplied by 1. So there is your final answer. That is 2 plus 2 root 3i to the power of minus 6. And we can see it's obviously a real number. It's got no imaginary parts. So there we go, we've completed the question. Okay, up next we're going to look at what's called Eulers Formula. So this is named after a very famous mathematician who discovered an alternative way of expressing complex numbers using exponentials. Okay, so our complex number, cos theta plus I sine theta, we can write this in exponential form as e to the I theta. Okay, so believe it or not, cos theta plus I sine theta is mathematically equivalent to e to the I theta. The proof of this statement is not quick and not simple, so I don't want to overload this video, but if you consult your textbook, it should be in there somewhere, but it's pretty gnarly. Okay, we can take both sides of this equation and we can multiply it by our modulus r, and there we have an expression for, on the left-hand side, we have a complex number in polar form. On the right-hand side, we have an alternative form, r e to the I theta, and this is called the exponential form. Okay, the relationship between these two is what's referred to as Euler's formula because he discovered it. Very smart boy. Okay, so it's nice because it's just a simple way of expressing a complex number. So we know that when we have an I in the power of our exponential, whatever is multiplying with that I is our argument, our angle, and whatever is multiplying at the front is your modulus. So it's just a different way of writing the same thing to maybe make some stuff look cooler. Okay, now having this form for a complex number in exponential form allows us to do some really freaky cool math stuff. Here's a couple examples. So first of all, we have e to the I theta equals cos theta I sine theta, as I previously stated. Now we're going to look at e to the I pi. So we're going to make the value of theta equal to pi. Okay, on the right hand side, we have cos of pi. So cos of 180 degrees is -1. Sine of 180 is 0, so that I is going to cancel out. And we're going to have e to the I pi equals -1. We're going to bring this -1 over to the left-hand side of the equation, and we're going to have e to the I pi plus 1 is equal to 0. So we get this really cool result that's often referenced as the most beautiful equation in all of mathematics. It's a lovely, simple equation that links the 5 most important numbers to human civilization. E, I, pi, 1, and 0, all in one equation. I don't know, I think it's cool. It's just a beautiful bit of mathematics and it looks made up, but it is actually true. It's real stuff, which is with imaginary maths. Okay, some more cool stuff we can do with imaginary numbers, or at least stuff that I think is cool, is we can once again take our identity from before, and this time we are going to substitute theta is equal to pi on 2. So on the right hand side we have cos pi on 2 plus I sine pi on 2. Now cos pi on 2 is cos 90. If I picture my cosine curve in my head, I can see cos 90 is 0, and I can see that sine 90 is equal to 1. Or you can fudge that with a calculator. So on the right, we get 0 plus 1i, so we get e to the I pi on 2 is equal to I. Okay, now what we're going to do is we're going to swap the sides, and we're going to raise both sides to the power of I. Okay, so we're trying to compute the value of I to the power of I, just for fun, really. On the right-hand side, hopefully you know that when we have a power of a power, the indices are going to multiply through the brackets. So we're going to have I squared pi on 2, which is going to be negative 1 pi on 2. So we get I to the power of I is equal to e to the minus pi on 2. Now, why I think that's interesting is because e to the minus pi on 2 is just a number. It's something that I can grab a calculator and just chuck in and get an answer. So you take this cool imaginary number, you raise it to the power of itself, and you get an answer of about 0.2. It's a bit anticlimactic, but it's interesting. Definitely, if you take an imaginary number, raise it to the power of itself, you can get a real answer, and it's just something like 0.2. I don't know, I think it's cool. Okay, for our next example, we are going to convert to exponential form, and then we're going to find z to the power of 5 in Cartesian form. So a lot of converting to be done in this question. First thing first, I want you to draw a picture of minus 1 plus I, because we're going to need to turn that into polar form, so we can figure out our modulus and our argument, so we can write it in exponential form. Okay, if you drew a picture, you would see that this complex number has a modulus of root 2 and an angle of rotation of positive 3 pi on 4. So here's our number in shortened polar form. Now we have our r and our theta, we can write it in exponential form, looking kind of similar. So we have root 2 e to the I times 3 pi on 4, which I'm just going to write as 3i pi on 4. Doesn't really make a difference. Okay, now we can use this form if we wanted to find the value of z to the power of 5. So taking both sides and raising them to the power of 5 looks like this. Now over on the right hand side, we're going to do root 2 to the power of 5, and we're going to once again multiply our indices through the brackets. So root 2 to the 5 and e to the 15 I pi on 4. Now let's simplify this a bit before we convert it back into polar and then back into Cartesian form. So root 2 to the 5, if we multiplied this 5 times, we'd end up with 4 root 2 after we simplify. Now once again, our argument, 15 pi on 4, is going beyond the range that we need it to be. I like to draw a little picture and think about we're doing 15 quarters of pi in the positive direction. So we're going to go 1 quarter, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, it's going to end us up down in this quadrant here. So rotating in the positive direction, 15 quarters, is actually just an argument of 1 quarter pi in the negative direction. Okay, that's why I've changed the argument from 15 pi on 4. I've instead written negative pi on 4 for that reason there. Okay, now we have our simplified version in exponential form. Now we can write it in polar form. So we have our modulus out the front, and we have an argument of minus pi on 4. Now we're going to convert into Cartesian form. Okay, so cos of minus pi on 4 is going to be cos of pi on 4, which is cos 45, which is 1 over root 2. Once again, sine of a negative angle will pull the negative out the front. So we have minus sine pi on 4. Same value, we get minus 1 over root 2 multiplied by I. Okay, now if we expand out the 4 root 2 at the front, we're going to end up with the root 2's cancelling each other out, which is nice and convenient. We'll have a final answer of 4 minus 4i. So there is our z to the power of 5 in Cartesian form. Okay, for our next example, we are trying to find the smallest possible value of theta, such that e to the I theta multiplied by e to the 2I theta is equal to I. Okay, this is a pretty strange looking question, but there's actually a fairly easy solution if you know the right path to take. So a good thing to know about complex numbers is they're much easier to compare when they're both in the same form. What I mean by that is if you have two complex numbers in Cartesian form, they're very easy to compare. If you had two complex numbers in polar form, similar thing. So in saying that, the left-hand side of our equation are complex numbers and they're written in exponential form. So the smartest thing we can do here is we can take the right side of our equation, which is I, and we can write this in exponential form. Okay, so we're going to find the modulus and argument of the complex number I, which if you think about your argand diagram, it's just one unit in the vertically straight up direction. That was good maths. Okay, so I as a complex number has a modulus of 1 and an argument of pi on 2. So writing I in polar form would be 1 cos I sine pi on 2, which means in exponential form, it would be 1e to the I pi on 2. Okay, for the left-hand side, we can simplify a bit because we are multiplying and we have a base of e. So we can add together our indices and have I theta plus 2i theta is going to be 3i theta. So left-hand side looks like e to the 3i theta. Right-hand side equals e to the I pi on 2. Now we can compare both sides of this equation and say if these are going to be equal, well, we have an e on both sides. We have a power of I on both sides. This must mean that the 3 theta is equal to the pi on 2. Okay, so by turning the right-hand side into the right form, and like I said, it makes comparing the two sides much easier and we can solve relatively easily. The reason the question says the smallest possible value of theta is because pi on 2 would work, but also the next lap around the circle would also work. So we could have 3 pi on 2, 5 pi on 2, so on and so forth. We just need the smallest one, so we just need pi on 2. Okay, final step is to divide both sides by 3, and we end up with theta is equal to pi on 6, and there is our answer to the question. Okay, up next, we're going to look at an HSC question from 2019. It's a band 3 multiple choice question. We have Z is a complex number with a modulus of 2 and an argument of pi on 3. Which of these four is equivalent to Z conjugate to the power of minus 1? By all means, pause the video and see if you can figure out what your guess would be before I run through my solution. Okay, so my approach here is I'm going to think about the conjugate of Z, and then I'm going to apply the power of minus 1 using de Moivre's theorem. So as we saw in a couple of previous videos, the conjugate of Z graphically is going to be a reflection across the real axis. What this means is that if Z has an argument of pi on 3, it means the conjugate of Z is going to have an argument of minus pi on 3. Okay, so we're just flipping across that real axis, going from Z to Z hat or Z conjugate, still having a modulus of 2, but now our argument, the sign has changed. Okay, we're going to keep it in polar form so that we can apply our de Moivre's theorem by raising to the power of minus 1. So we have Z to the minus 1. So that means we're going to do our modulus, so 2 to the power of minus 1. And then we're going to multiply our modulus by minus 1. So the modulus was already negative, so if we multiply it by negative 1, it goes back to being positive, pi on 3. Okay, 2 to the power of negative 1 is going to be 1 over 2, so we have a half out the front. We have an argument of pi on 3, which looks exactly like option C. Well done if you said the same thing. Okay, and to finish off this video lesson, we're going to do a challenging question. We have, given that n is an integer, so a whole number, simplify the expression 1 plus I to the 8n plus 1 minus I to the 8n. If you're feeling really confident, by all means pause and have a go. Otherwise, I'm about to roll through my solution. Okay, so because this was a lesson primarily focusing on de Moivre's theorem, that's what we are going to do to handle this question here. We're going to turn both of these complex numbers, 1 plus I and 1 minus I. We're going to write them in polar form so we can apply de Moivre's theorem with a power of 8n, where n is a whole number, and see what we can simplify using some clever maths. Okay, so 1 plus I, if we drew a picture, we'd see a modulus of root 2 and an argument of pi on 4. 1 minus I, we would see root 2 again, but our argument would be minus pi on 4. Okay, so to raise both of these complex numbers to the power of 8n, we're going to raise the right-hand side using, of course, de Moivre's theorem. So the first one to the power of 8n plus 1 minus I to the 8n, we're going to have our moduli out the front, the root 2's, raised to the 8n, and our arguments are being multiplied by 8n. Okay, so there's our De Moivre's theorem applied. Now the challenging part of the question is, now we need to express the right-hand side in the simplest possible way. Okay, so a few tricks we can use here is, once again, for like the third time today, we can use the cos of a negative angle is going to be the same thing as cos of a positive angle. That's going to be convenient. And of course, sine of a negative angle, we can once again pull the negative out the front and have minus I sine 8n pi on 4. We can also simplify the fractions. 8 over 4 is going to be 2. So all of these angles we can write as 2n pi. And that's what we've done there. Okay, now we're going to expand. And what's convenient is in the left-hand bracket, or the first bracket, we have positive I sine 2n pi multiplied by root 2 to the 8n. Over on the end, we have root 2 to the 8n times minus I sine 2n pi. So we have really the same term at the front and the back, except one is positive and one is negative. So when we expand these brackets out, these sine terms are going to actually completely cancel out and make it much more simplified. Okay, so the sine terms are cancelling out. We're just going to add together the two cosine terms. So we're going to write root 2 as 2 to the power of a half. So we can apply these powers and do a half multiplied by 8n. Okay, we're going to need some more room for that. So there was our last line. Now we're going to have, okay. So right here we have 8n multiplied by a half is 4n. So these front terms are both turning into 2 to the 4n. And now because we have the same thing adding to itself, well, imagine if you were doing x plus x, the answer would be 2x or 2 times x. We have this term adding to itself. So simplifying it, we're going to have 2 lots of this term, okay? 2 lots of them adding together. Now let's think about cos of 2n pi. What do you know about cos of 2 pi? Again, if you close your eyes and picture your cosine curve, you should see that at 2 pi or 360 degrees, the value of cosine is equal to 1. Okay, now because n is a whole number, this could be 2 pi, or it could be 4 pi, or it could be 6 pi, it could be 8 pi, it could be all the multiples of 2n. Okay, the good thing about those multiples is that's all the points where the cosine curve repeats. So cos of 2 pi, cos of 4 pi, cos of 6 pi, they all have the same value and they're always equal to 1. Okay, so because n is equal to an integer, this is going to be a multiple of 2 pi, and at any multiple of 2 pi, the cosine curve is always equal to 1. So we have 2 times 2 to the 4n times 1. So we can just ignore the times 1, and we can think of this as 2 to the 1 times 2 to the 4n. So we get 2 to the 4n plus 1 as our final answer. Okay, pretty gnarly, but if you know the right tricks, you can tidy it up pretty significantly and have a really nice, fully simplified answer for our expression. Okay, cool. Thanks so much for watching this video. Hopefully you learned some knowledge. I'll catch you guys in the next one. See you later. Bye.